Hello there. Welcome to the Learning of Engineering tutorial video lectures. In this video lecture, we are trying to determine the crippling load. From the series of video lectures we are making on this, the crippling load calculation, when a column is going to be subjected to the axial loads. That axial load either may be the compressive load or maybe the tensile loads. In this case, we are doing specifically for the column. The definition of the column here is the axis of the member must be vertical. And in this case, what will happen? That either one end is going to be fixed, other end is going to be the free, or some other cases also that we have seen. And today we are going to see, we are calculating the crippling load when one end of the column is fixed. That means one end is going to be the fixed, other end is hinged or pinned. We know when one end is fixed, its degrees of freedom is going to be different, and when the hinged or pinned, its degrees of freedom is going to be another one. So there we can see this figure, these statements are going to be illustrated over here. There we can see I have taken the axis of the column, the cross section is going to be the constant. So then A is going to be the fixed end and the B is going to be the hinged or pinned we have taken. At the same time, some axial load is coming to this member. That load I am going to be considering as a crippling load, and it has the length, it is there. So then how could you determine the crippling load? That's the magnitude we need to be defined in terms of the certain characters. As we know, when the load is coming to this member, so then what will happen to this? We know this member will going to be start to bend. If bending is not there, there is no calculations over here. We have to assume that there is a bending is there. So there is two types of bendings are going to be available. One is going to be the bending like this. Another one is going to be bending like this. So there we can see when I am going to be taking the axis of this member, right? So in this case what will happen? One end is going to be the fixed end is there. Another end is going to be hinged is there. But these kind of the bendings generally it will come. The one end is going to be the free end only, it will come. So now our assumption is that the bending of this one, that's going to be buckling, we are going to be calling, it's going to be taking like this. Alright, so this is only the assumptions we are going to be taking, and it is going to be, effect is going to be generating, buckling effect. As we know, we need to understand here, at the end A and end at B, so then the deflection is not going to be available, but only at the middle of the span is going to be available. We know at end A, that's going to be the deflection y is equal to 0. Similarly, the slope also going to be 0. That's going to be dy by dx is equal to 0 at A, comma B. Right? So then how could you calculate the crippling load? For this one, we need to take the deflection existed on the beam. So at certain point, I'm going to be considering, this is the point C. Alright? So then what happened? It is located at a distance of x from the end A, and similarly y from the axis of this member. Right? I am going to be considering the x and the y is nothing but the deflection of the member. Right? And this length from this side is going to be L minus x we do have. So whatever the calculations we are doing with respect to C only we are going to be doing. So we know that the differential equations, before that we need to go here with the moments we have to be considered. The moments due to the load P, right? And due to this load, there is going to be the reaction forces are going to be generating. That's going to be the M naught is going to be, that is going to be the moments at the fixed end. And similarly, because this is the hinged end, this is the reaction force is going to be generating to control or to resist the deflection at the end A. And similarly, there is a reaction force also going to be generating at the B. That's going to be, I am going to be say the H is going to be the reaction force. That's because of the fixed moments. So this is going to be counterbalanced over here by with the horizontal reaction force. Now what I'm going to do, I'm going to be taking the moments at C. So then we can see how it is going to be happening. So there we know that the moments at C is equal to, what is the formula? So here can you see the two forces are going to be acting over here. So one is going to be moving in the clockwise, another is going to be anti-clockwise. That I am going to be taking h into L minus x. Can you see? This is going to be the line of action and this is the perpendicular distance to the point C. That's going to be m is equal to h into L minus x minus p into the deflection I am going to be considering. So this is going to be the moments at C. And similarly, there is going to be another moments also we are going to be considering. That's going to be mc is equal to here ei into d square y by dx square. This is the standard equations we are using for identifying the crippling load over here. So what I am going to do, I am going to be equating these two. So I am going to be taking ei d square y by dx square is equal to h into L minus x into minus py we are going to be considering. So now that equation what we got it, so that I am going to be taking to the one side to other. So that's going to be d square y by dx square minus will be going to be here the p into y, and ei I am going to be taking here ei, that is equal to h by ei L minus x, we got it. So this is the simplification we are doing, and further simplification also we are going to be doing here by introducing the crippling load over there. So in order to develop the differential equation, further modification it is going to be here d square y by the dx square is plus p by ei into y, that is equal to, I am going to be taking h by, so in this case h by ei I am going to be multiplying and divided with the crippling load over here, that's by p, that's going to be L minus x, right, L minus x. Further simplification of this one, the d square y by dx square plus p by ei into y is equal to, that's going to be p by ei into h by p L minus x, we got it. So now I am going to be writing the differential solution equation I am going to be writing. So that I am going to be taking from this one the differential solution equation, the differential solution. So how could you write here the differential solution here? So that is equal to y is equal to, after the integration of this one we are going to be writing y is equal to the C1 into, so what is the formula we have here? The cos x into the square root of p by ei, we got it, right? So the cos into x into square root of p by ei plus C2 into the sine x into the square root of p by ei, we got it. And similarly we do have the terminology over here p by e into h by p. Now I am going to be taking h by p, this terminology, plus h by p L minus x, we got it. So this is going to be the differential solution equation after the integration. In this case the two terminologies are there, that's going to be C1 and the C2 are the integral constants. We know how to solve it. So what I am going to do, I am going to be substituting the boundary conditions of this one at A as well as at B. So by using these two, I am going to be, here in this case x terminology also there. At the point A, x is equal to 0, right? At the point B, x is equal to L we do have, right? So but the deflection as well as the slope are going to be 0 over there because of they are going to be rigid system is going to be. So now I am going to be substituting the boundary conditions at A in this first equation, and the later I am going to be substituting the boundary conditions at B in this equation so that I can calculate the C1 as well as the C2. Now this is the equation we got it. Now we need to substitute the boundary condition where we are going to be find C1 as well as the C2. So now I am going to be taking x is equal to 0, y equal to 0, because in this equation two variables y and x only available. So when y is equal to 0 in this equation, it will going to be 0. C1 into the x is equal to 0. That means cos 0 into square root of p by e also we are getting the 0, plus C2 into the sine x is equal to 0. That means the sine 0 we are getting, plus h by p L minus, what is the x value here? That's going to be 0. So that we got the 0. So then we know cos 0 is equal to 1, sin 0 is equal to 0. So when I'm going to be substituting, this total parameter is going to be 0, and then I got the C1 is equal to minus HL by P, I got it. So it means we have calculated one integral constant, that's going to be the C1. So now what I'm going to do, I'm going to be deriving this equation with respect to the x, so that I can substitute these slope values also, then I can calculate the another parameters. Now we are doing the differentiation. This is the parameter I am going to be taking, dy by dx, that is equal to, the C1 is the common. What is the cos theta? The cos theta, the derivation is going to be minus, we are getting minus sine x into the square root of p by e. And similarly, xp is equal to the square root of p by e, because it is going to be the constant. And similarly, the C2 into sine will become cos theta. Here x, the square root of p by ei, we got it. And similarly, this parameter also we have to do the derivation. So that's going to be the square root of p by ei, I got it, plus here h by p into L, suppose, and this will going to be, I can write it here, hl by p minus hx by p, I got it. So then what happened, this parameter will going to be 0, right, and the x is going to be, it will going to be the one time. So that I'm going to be writing here, that's going to be minus h by p, we got it. So now what I'm going to do, I'm going to be substituting the values of x is equal to 0, and similarly dy by dx is equal to 0. If I'm going to be taking the slope, and these two are only the variable, so that if I'm going to be substituting in this equation, so then what will happen, dy by dx is equal to 0, alright. So then we know the C1 is equal to minus, that's going to be how much we got it. So now I'm substituting minus C1 into the sine theta. The sine here x is equal to 0 here, I'm substituting, this will become 0, and square root of p by ei, plus C2 into the cos, x will become 0 here, so cos 0 we are getting, and square root of p by ei minus h by p, we got it. So then what happened, sine 0 is equal to 0, cos 0 is equal to 1. So then what I'm going to do here, this parameter will going to be vanish, and right, it is only existed here, that's going to be C2 square root of p by ei is equal to minus hp is equal to 0, h by p is equal to 0. So I'm doing the further simplification, that's the C2 is equal to h by p, I took to the right side, and then this will become ei by p, we got it, right, that I'm writing here, the C2 is equal to h by p square root of ei by p, we got it. Now we have calculated the C1 as well as the C2. So now what I'm going to do here, I'm going to be introducing the second boundary conditions. Now I changed the equation 1, right, into, after getting the C1 and C2, I have substituted in this equation. Now I'm going to be introducing the boundary conditions at B. We know x will become L and y becomes 0, right, this is the total length we are getting, and here y is equal to 0, it means that the deflection at the point B is 0. Now I'm going to be substituting in this equation. So what I'm getting, y is equal to 0 means this equation, this is going to be 0 minus h by p, and cos x will become L square root of p by ei plus h by p square root of ei by p sine here L into square root of p by ei, we got it, right, that's going to be ei plus h by p L minus L we are getting, because x will become L. So that means this parameter will going to be 0. So now I'm going to be reshuffling of this equation to the left side as well as to the right side. The first I'm going to be keeping h by p square root of ei by p sine L into square root of p by ei we are getting. That is equal to h by p cos here L square root of p by ei we got it. So there we can see here. So what I am going to do here, h by p is going to be the same magnitude, it is going to be cancelled out. So then what I am going to taking sine theta cos theta we had. So that I am going to be writing sine by cos is equal to the tan L square root of p by ei we are getting. That is equal to here, I am going to be taking to the right side of this equation, that I am going to be here, that's p by ei we are getting. So can you see, this is going to be the simplified form of this equation. So now what I am going to be introducing, we know the solution to the above equation we are writing. So now I am going to be taking the tan to that side, and we are going to do simplifying this equation, L into the square root of p by ei. So that is equal to 4.5 radians, right? I am going to be taking here is the directly, that's going to be 4.5 radians we are getting. Once we are getting the 4.5, so that we need to be calculate the value of the phi from this equation. So the further simplification here, that's going to be L square root of p by ei into 4.5 we got it. Now what I am going to do, I am going to be squaring on the both sides. The squaring on both sides means here, or we can do here like this, that's going to be square root of p by ei is equal to 4.5 by L we got it. This square terminology will comes to over here. So that what I am going to be getting here, that's going to be p by ei is equal to the 4.5 whole square. So that I got it here around 20.25 divided by L square we got it, right? That's going to be 20.25 by L square we got it. Now I am going to be taking over here is the p. So the p is equal to 20.25, that is equal to ei by L we got it. So this equation we are going to be writing, this is equal to, suppose that's the p is equal to 2 pi square ei by, sorry, here is the L square. So then we are getting the L square here. So this is going to be the magnitude of the crippling load that we have mentioned in terms of the mathematical model, right? Accordingly, the P is directly proportional to your Young's modulus, P is directly proportional to the moment of inertia, and P is inversely proportional to the square of your length of the system. So this is the crippling load when the member one end is going to be the fixed, other end is going to be the hinged, and the load is acting in this axial direction. So I hope you are able to understand how to develop a mathematical model for analysis of a column when it is going to be subjected to the axial loads, and the boundary conditions are like this: the one end is fixed, other end is going to be hinged or pin end. So I hope you are enjoyed the derivation of this equation, and still if you feel any confusion, please put in the comment section so that I can reach you out. Thank you.